Welcome to BKW Physics. I'm Mr. McConnelly. We're going to talk about the left-hand rules of magnetism. There's a man named Hans Ørsted in 1820. He was setting up an electric circuit. I don't know what he exactly had with the electric circuit, what it was, but I've just drawn a battery and a resistor. And so there's electrons flowing around this circuit, and what he noticed is that when he brought a compass, like a north, south, east, west compass, when he brought a compass close to the electrical circuit, the compass didn't do what he would expect. Like if he held the compass over here, it would say, oh, that's north. But then when he brought it close to the circuit, it wouldn't point that way anymore. It would like change the direction of the compass. And he said, I think I'm onto something here. And he started investigating. And so I'll just draw that, you know, if this is normally north, now the compass is like pointing kind of the wrong way for your notes. So you can realize that what he was seeing is that the compass was somehow being affected by the circuit. All right. So then he went into a little more detail and he set up something like this. He isolated one of the wires of the circuit and he ran it through a piece of cardboard, we'll say, or wood or something. And so if we say that the current in the wire, remember current is the letter I, if the current in the wire is flowing upward at this point, he found that this compass would point this way, this compass would point this way, this compass would point this way, and this compass would point this way. So he started to see a pattern emerging here. And what he eventually came up with is what is called the first left-hand rule. Of magnetism. And it goes like this. Your thumb of your left hand, we're talking about your left hand here, your thumb of your left hand points in the direction of the current, or the electron flow. Thumb is I/electron flow direction. So you point your thumb in the direction of the current or the electron flow. Got it. So I'm pointing my thumb on the picture. I'm pointing my thumb just so it's pointing the same as I have it drawn, up. And then your fingers, I'll say curl in the natural direction, because I know there's somebody watching the video or in this room that can like bend their fingers the wrong way around backwards, but I can't. So, okay, there he is. But I'm talking about people, normal direction, your fingers tend to like to curl this way, okay? So let your fingers curl in the natural direction. And what that tells you is that tells you the direction of the magnetic field. So let's look at that. Let's play it out on the picture. I take my left hand. It doesn't matter which side of the picture I stand on. I can do like this, or I can do like this. To see my thumb either way is pointing up. So I'll stand here so I'm not blocking the words. So my thumb is pointing up like this. And now I just allow my fingers to curl around the wire in the natural direction. You kind of have to visualize this maybe in 3D. Some of you might have trouble with that. So if this is the wire, this green meter stick, or actually it's a yardstick, but if this is the wire, and I point my thumb in the direction of the electrons, and my fingers are wrapping around the wire this way, and this way that my fingers are showing is going to be the direction of the magnetic field. So if I draw this all out, the magnetic field will go something like this. It'll cut behind the wire. And that's what his compasses, Hans, when he did this experiment, his compasses were indicating to him that the magnetism was like circling the wire. Now the closer to the wire it is, the stronger this effect is. As you get away, further away, it gets weaker, and if you back pretty far away, now you don't notice anything, and the compass goes back to pointing in the Earth's magnetic field just north. Okay? So let's do another example and see if you can follow what's going on here. I'll let you try to figure this one out. So what if I drew a picture like this? I have a battery. And I'm gonna draw a big piece of cardboard here. And in this example, I'm gonna come up through the bottom of the cardboard here. I'm going to drop back down through the cardboard and return to the battery. Let's put a resistor in there so we don't short circuit the battery. Okay. So in this case, I want to know what direction is the magnetic field between the two wires on the piece of cardboard. So how do we approach this? Well, step one, we have to first determine which direction is the electron flow in the circuit. And we determine by looking at the battery that the electrons, the short end of the battery usually indicates the direction of the out. So the electrons are flowing, we'll call it clockwise on my particular picture. Alright, so when we get up to here, we can think about the electrons flowing that way. They're going to wrap around, the electrons are going to flow this way. There. So we've established the direction of our electrons. Now we got to fire up our left hand. Everyone fire up their left hand. We put our thumb in the direction of the electron flow. I'm going to do it from this side this time. So at this point, the electrons are going up through the cardboard like this. I allow my fingers to wrap in the natural direction. So it's just like the picture we did a second ago. The magnetism is going to be like that around the wire. But take it a little bit further. If we follow the electron to this point, now notice your thumb is pointing down. So your fingers are wrapping in the natural direction of this. The magnetism is like that. I'm going to erase my question right here. So if we extend it out a little bit, you can see that if I draw another. Would you agree on the left hand that the arrows will be going this way because all the arrows are going to be going around like that? And on the right hand side, you might be able to see that the arrows are going to be going that way. Can you visualize that? So what was happening right in the middle then? Now, remember, I didn't mention this in the last video, but magnetic field lines cannot cross one another. So when they meet in the middle here, they're not going to cross. They're going to kind of join forces and run parallel to one another.
But they can't cross.
They can't cross.
But they can like.
They can come close.
But they can't.
They can't cross. Okay? And when they come close, they're going to be stronger. So what's going to happen right here is you can see that the magnetism is basically, well, it depends how you're looking at this 3D picture. If you're thinking this cardboard is flat, it's coming towards you. If you're thinking this cardboard is tipped, it's going down. But you can kind of see from the arrows the direction of the magnetism. Now, by the way, magnetism, remember how current was an I? Magnetism is an inconvenient letter also. It's a B. Okay? So the letter for magnetism is a B. Well, that's the first left-hand rule. But there's more left-hand rules. Let's move to another one. Second left-hand rule. The second left-hand rule applies if you coil wire, which we also call the solenoid. That's the name for a coil of wire. When you coil wire up, we call it a solenoid. So if we did something like this, if we had a battery, and we had a piece of iron here, like a nail. You took a nail. And then you took the wire and you wrapped it around the nail. Anyone done this before? No one's wrapped a wire around a nail?
Oh, I have.
Oh, okay.
I think James
Oh yeah, James did that a lot last year. I actually have one over here. Let me just pull it out so you can kind of see. So I was playing around with this, and I just took a normal See that? A nail. Iron nail. I wrapped a wire around the nail. And when I do this, if I hook this to a battery right now, you know what it does to the nail? It makes it a magnet. We'll talk much more about that on another lesson. But basically, what I'm drawing here for you is this example. I'm showing you that you can wrap a wire around a piece of iron, hook it to a battery, and you're going to get a magnet. But my question is, which end of the iron is the north and which end is the south? And that's where the second left-hand rule comes in. So here's what you do. On the second left-hand rule, you start with your fingers, and your fingers follow the electron flow. And you're like, wait a second! A second ago you told me that my thumb was supposed to follow the electron flow. Yeah, that's true, but that was on the first left-hand rule. See why this is confusing and see why I'm presenting them at the same time? So, on the second left-hand rule, your fingers follow the electron flow, and on the first left-hand rule, your thumb follows the electron flow. You just gotta know that. Alright, so, we follow the electron flow. So first of all, we gotta establish that the electron flow is this way. Okay, good. There's our electron flow. What are we doing? We're following that with our fingers this time. So forget about your thumb now. Just follow it with your fingers. We follow it with your fingers. Here we go, here we go. Okay, now, when we get to the part where it starts coiling around, basically what you do is you just follow with your fingers. Now again, I know some of you can probably wrap your hand backwards around a piece of metal, but I can't. And so what I want you to do is imagine that once you get to here, you got to decide which way to turn your hand, because your hand could be either way. But you're going to turn your hand this way because see how you want to wrap your fingers around? You're trying to follow the electron flow, and the electron flow goes behind the piece of metal, so you're just going to wrap your fingers around. When you wrap your fingers around, see how your thumb's left pointing? Your thumb indicates or tells you where the north is. So your thumb will actually indicate or tell you where the north of this magnet is. So let's do it. We're trying to decide, we just don't know which way our hand should go. When we get up to here, we're like, oh, my fingers have to wrap around, so boom, there's the north. If this is the north end, then this is the south end. And if that's the case, and we wanted to draw some magnetic field lines, the magnetic field lines from last lesson would be from the north to the south. So the magnetic field lines would look like that. You don't really need those on the picture. I'm just trying to give you the whole idea of this. Okay? So that is the second left-hand rule for today, physics.